All right, so we've done chapter 1. We talked a little bit about what data is basically. And now we have to talk a little bit about probability. So we'll go through that, and that'll be today. I know you all know what I'm talking about. Google search results obviously tell me a little more about, probably tell you more about me than I want them to. You know what probability is on some level. And just out of pure nostalgia's sake, I went to ask.com, which I don't think you guys even knew existed probably. It was a big deal a long time ago, about the time you were born, maybe. Anyway, I guess it still exists. I didn't know it did, but it doesn't have any search history from me. So there's a kind of a better, maybe a better sample of what people ask about. But I do notice people wonder about the lottery. The probability is not good. It's not good. I can tell you that. I don't know what it is. I would apparently be a gambler, but that's what Google must think of me. Anyway, I bring this up just to show that it's in the common parlance. It's something we commonly say. You know, what's the probability of? Even though you may not really mean what's the probability of when you say it, but it's something we say. So what is probability? We need to narrow this down. The probability of an outcome is the proportion of times the outcome would occur if the random phenomena could be observed an infinite number of times. Feels heavy, doesn't it? Like there's a lot in that. Okay, so we're talking about a proportion. Let me make sure. And as such, you know, you're thinking about how many times out of something else does this thing occur, whatever this random phenomena is. As a proportion, it will fall between 0 and 1. 0 being probability 0, meaning there is no probability. There is no probability of it, basically, or 1 that it happens with certainty. It can also be expressed as a percentage. And I think that's a little more of maybe a little more natural. Different people's minds work differently. So just be careful whenever you're filling things in on your questions. And make sure that you're labeling it according to what the question is asking for. Because it could be asking for a proportion, in which case it would be like 0.50. That would be half, right? And if the same question could be answered 50%. So just be sure you're labeling appropriately. So the probability of rolling a 1, maybe on a dice, we can use the letter P to note probability, and we can put parentheses behind the P and say rolling a 1. Now, admittedly, you needed a little bit more context there. You needed to know that we were talking about die. So, notation can be further. It could be we can abbreviate it. So if the process that we're talking about, again, it needs to be clear. So you're going to have to write this down sometime. The probability of rolling a die, if it happens to be a 1, we can actually just write it as P of 1. So P parentheses 1. Just as long as we know that the context is clear, you can do P parentheses 1. Not a huge deal. Most of the time, we're not dealing with the kind of limited space where that's an issue. I think on Thursday, we'll do more examples and homework and stuff. And there you'll see, assuming we get done with all this today, if y'all interrupt me a lot, which is great. So you have a lot of questions and feedback and stuff like that. Then we might not, but if we do, then we do. So it's all good. You might see a time when it would be advantageous to do something really abbreviated, like a P of 1, rather than writing out P rolling at 1. So we can also note the event itself. So we can call the event A. We're just assigning it a letter. And if event 1, or for event A is rolling a 1, then we might just say the probability of A. And that's a nice way of, again, it's just an easy way of defining things that are maybe messier. And again, especially whenever you get into more complex statements, it might become a little more useful. And also, for the sake of notes and stuff, we sometimes refer to things as events A and B. And then you might have to look somewhere else to look and see what event A is and event B is. But it makes the math a lot cleaner looking if you're not having to look at all of the words at once. So that's that notation. All right, so we have some definitions. An experiment is a process that, when performed, results in one and only one of many observations. So I could roll a die, and or flip a coin. Well, every time I flip the coin, I have an observation, heads or tails, heads or tails, every time I flip the coin. And those are outcomes, the heads or the tails or the number if it's a roll of the dice. And the collection of all of the outcomes is what we call the sample space. If our experiment is to toss a coin once, we have possible outcomes of heads and tails. So then our sample space, S, head, tail, whatever. Maybe you toss a coin twice, heads. These are all the possible outcomes. So sample space would be the possible outcomes of your experiment. We have a statistical law that we, thank God, don't have to prove because we're not in that kind of math class. As more observations are collected, the proportion, so the p hat there means that it's an estimate of a proportion. So we're estimating something that we're sampling, and with a particular outcome converges to the probability of P of that outcome. Okay, so what am I getting at here? If I hand you a coin and you're concerned about it being a fair coin and you want to flip it, if you flip it twice and you get both tails, is the coin biased? Do you think the coin is bogus? Do you think something's wrong with it? Just out of twice? No, I mean, you've only flipped twice. Flip 100 times and it's tails every time? Now we're talking, because you really ought to be approaching something close to 50%. Because you have two sides that are equally likely. So we should have roughly an outcome of 50% heads and tails. So, does that make sense? Again, if you just flip it twice, that's pure chance. As you approach infinity, you're going to get closer and closer to that 50% number, if assuming it's the right number. I want to see somebody challenge a coin toss with that. No. we need to increase the number of tosses as it approaches infinity. No. Okay, so we have some more terminology. Disjoint or mutually exclusive outcomes. Two outcomes are disjoint or mutually exclusive if they cannot both happen at the same time. Okay, so when rolling a die, the outcomes 1 and 2 are disjoint. They can't both happen. However, the outcomes 1 and rolling an odd number are not disjoint because both occur if the outcome is a 1, right? So that's, and this kind of feeds into how we're going to calculate the probabilities of these events. So here is a diagram. Events A, B, and D consist of outcomes from rolling a die. And we can define A as rolling a 1 or a 2, event B as a 4 or a 6, and event D as a 2 and a 3. So A and B are disjoint because they don't have any outcomes in common. But A and D are not because they have outcomes in common. They overlap at 2. So where we're headed with this is that mutually exclusive outcomes, we can calculate these probabilities if through what's called the addition rule. So if you wanted to know the probability of A or D occurring, they're independent events, and we can use the addition rule. So, and basically by adding together the probability of A and the probability of B, we get the probability of A or D. And that's what the addition rule tells us. So what is the probability of rolling a 1 or a 2? Okay, well, on a die, the outcomes 1 and 2 are disjoint. This is separate from the A, D, B example. Now we're on to just a quick example on these numbers being alone. So when rolling a die, outcomes 1 and 2 are disjoint, then that means that the probability of all of these outcomes will occur is computed by adding their probabilities. So the probability of 1 or 2 is equal to probability of 1 plus the probability of 2, which is equal to 1/6 plus 1/6, which is equal to 1/3. And that's exactly what I would do if I were you for the homework or exams or whatever. Whenever you're doing these probability questions, is write it out so that you have that first statement. What am I calculating? Okay, probability of a 1 or a 2. Do you need to be all really verbose in that statement? Of course not. You just need to know what you're talking about. Then write in the formula for finding the probability of what you're doing. So in this case, remember, you just say, okay, this is an independent event, or these are independent events. So this is an OR, and it's an OR statement. So that means I'm using the addition rule. So I go look up what the addition rule is, and I say P of 1 or plus P of 2. Then I fill those in, 1/6 plus 1/6, and then simplify. And add it up and simplify. That makes sense as a process? Okay. It's really helpful if you go ahead and write that out. I know it takes some time and generally don't want to be doing statistics homework or exams any longer than you have to, but it'll help. So what about the probability of rolling a 1, 2, 3, 4, 5, or 6? Okay, well, first of all, for just a second, suspend the fact that you should already know the answer and be like, duh, it's like all of the choices. Okay, so probability of a 1, 2, 3, 4, 5, or 6. So those are all disjoint, and we can say P of 1 or 2 or 3 or 4 or 5 or 6. And then you write it out in the formula form here, and then you write out, put in the individual formulas or individual probabilities, and that equals 1. So you're going to, by definition of rolling it, you're going to roll one of those numbers. Okay. We can also have these non-disjoint probabilities. So if you're thinking about something a little more complex, and you want to know about decks of cards, and so your regular deck of cards split into the 4 suits. You got club, diamond, heart, and spade. And each suit is has 13 labeled cards, 2 through 10, jack, queen, king, and ace. And thus each card has a unique combination of suit and label. So you can have a 4 of hearts and a jack of clubs. Okay, so if you wanted to say Venn diagram for diamonds and face cards, well, I mean, you have all the diamonds right here. And you have all the face cards right here. So 13 of 52 of those are diamonds. We just talked about that. There are 12 face cards because there's the 4 for each of the 3. Where's my aces? Right, not aces. 3 here. And I don't play cards, so I'm not really good at these. But they overlap. We got king, queen, jack for some of them. Now, in practice, what is the probability that a randomly selected card is a diamond? What is the probability that a randomly selected card is a face card? Okay, well, actually, I'm just going to skip this part of it. There are 52 cards and 13 diamonds. Okay. If the cards are thoroughly shuffled, each card should have an equal chance of being drawn. So the probability that a randomly selected card is a diamond, so P of diamonds, is equal to 13 of 52 equals 0.250. Okay. Likewise, there are 12 face cards. So P of face card equals 12 of 52, simplified to 3/13 or 0.231. Okay, so now we were just talking about these probabilities that were single. Diamonds or face or diamonds. That's it. No further part of that question. Or face cards, another question. Not a no and or statement in that. Now we can also we can generalize the rule, the addition rule, so that we don't have to worry about the disjoint piece. And we can say that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, where a probability of A and B is the probability that both events occur. So backing up right quick, if you're concerned, if you're thinking probability of diamonds or probability of face cards, then you have 13 of 52 plus 12 of 52 minus 3 of 52. So probability of diamonds plus the probability of face minus the probability of diamonds and face. Because if you don't take that piece out, you're double counting it. You're just going to subtract out the one of the times that the overlap has been counted. Does that make sense? You're still saying 13 of 52 and then 12 of 52 and then subtract out the 3 of 52. So that's what I just did here. So again, let A represent the event that a randomly selected card is a diamond, and B represent the event that is a face card. Events A and B are not disjoint. The cards Jack of Diamonds, Queen of Diamonds, and King of Diamonds fall into both categories. We need a general addition rule to deal with the double counting. So the probability of A or B equals the probability of face card or diamond. Probability of face card plus the probability of diamond minus the probability of face card and diamond. Okay. 13 of 52 plus 12 of 52 minus 3 52nds. And you can simplify that down to 11/26. Whatever that turns into for a decimal place. Does that kind of make sense? So this general addition rule, by adding the second piece here, the minus where the double counting is, allows us to think about these events where they're not disjoint, where there is some overlap in possible outcomes. Can come in handy. You might have thought about, and I wondered about shuffling this earlier in the slides. Remember that earlier, whenever I was kind of made fun of the slides for saying that the probability of rolling a die and getting a 1, 2, 3, 4, 5, or 6 was 1, and it felt kind of silly to actually make that calculation. Well, what it might be useful for is that you might use it to find a complement. So you have the probability of A, in this case, which might be, let's actually just go with the diagram here. The event is D, so you might find the event D, and then you want to know what the complement of that is. Well, the event D is a 2 and a 3. Well, then the event D complement, DC, as you know, see it noted there, 1, 4, 5, and 6. Okay, so it's everything that you define the sample space, so you knew what was possible, 1, 2, 3, 4, 5, or 6. Then you define your event, which includes only 2 of those outcomes, 2 and a 3. So then the complement is everything else. Okay. So, and then that means that the probability of A plus the probability of A's complement, that's what this is saying, is 1. So the probability of event D up here plus the probability of D's complement right here equals 1. Now, what's useful about that is that the probability of A is equal to the probability of 1 minus A's complement. So if you wanted to know the probability of D, and for some reason you knew, or you could easily find the probability of D's complement, that's an easier way of getting there. So you find the probability of D's complement and you subtract it from 1. 1 minus D's complement. Now I know the probability of D. Does that make sense? Again, it's silly whenever we're talking about only 6 choices, and they're all right there. It's only 1 of 6. It's all right there. When things get more complex, these rules kind of get handy. So the probability of D's complement of 1, 4, 5, or 6. Okay, 1 6 plus 1 6 plus 1 6 plus 1 6 is equal to 4 6 or 2/3. So what is the probability of D plus D's complement? 1, just as you would expect. Okay, so if you wanted to know what the probability of D is, then you can say 1 minus 2/3 and C. Probability of D is 1/3. And I didn't have to add anything up. Make sense? Okay. Now, what if two processes are independent? As in they have no bearing on each other. For instance, flipping a coin and rolling a die are two independent processes. Knowing that the coin lands heads up won't help with the outcome of the die roll. On the other hand, things that are maybe more complex, your stock prices tend to move up and down together to an extent. But, if the market's up, then individual stocks are probably moving up. If the market's down, then they're probably moving downward. So they're not independent, even if they're not like one-to-one correlated, where they, there's definitely a link between these. Just general directional moves together. That indicates that it's not independent. So let's have a green die and a blue die. So we have two die, and we can diagram them out like this. So 1/6 of the time, the first roll is a 1. Then 1/6 of those times, the second roll will also be a 1. So you have a green die or blue die, whichever one's first. 1/6 of the time, you have you roll a 1, and then you roll the other die, which has no bearing. The fact that you rolled a green die over here and got a 1 has no bearing on what's about to happen with the blue die in your other hand. So then for this, what we have is the multiplication rule for independent processes. So if A and B are represented from two different independent processes, then the probability that both A and B occur is given by the probability of A and B equals probability of A times the probability of B. If we make this a more complex event where there are, say, K events, so 3, 4, 5, 1,000, then the probability that they all occur, so probability of all of A through K occurring, is the probability of A times the probability of 2, or A2, so on until the end. So you just multiply all of those probabilities together, and that's how you find the probability of the and of all of those statements. So what if there was also a red die independent of the other two? So we have a green, a blue, and a red. What's the probability of rolling 3 die, and getting all 1s? Okay, well, the same logic applies. If 1/36 of the time both green and blue dice are 1, then 1/6 of the time the red die will also be 1. So the probability of blue equals 1, and green equals 1, and red equals 1 is equal to the probability of blue equals 1 times the probability of green equals 1 times the probability of red equals 1, which is equal to 1/6 times 1/6 times 1/6, or 1/216. Okay. Kind of makes sense in this kind of weird abstract world. So what's the event? And the event is the event of drawing a heart from the deck of cards independent from drawing an ace? The probability of drawing a heart is a quarter. So 13 over 52 equals 1/4. And the probability of drawing an ace is 1 out of 13. The probability that it is an ace is 1 out of 13. So because of the 4 over 52. Okay. So the probability that the card is the ace of hearts is 1/52. So is equation 229 satisfied? So if the probability of heart and times the probability of A is equal to 1/52. And then the probability of heart and A is the same. Since the equation holds, the event that the card is a heart and the event that the card is an ace are independent events. So we can, I think we'll have a question on this in homework that'll help. Okay, so we've done events on their own. We've done disjoint events where they don't have anything to do with each other. We've done non-disjoint events where they don't have anything to do with each other. So we're 4 statements here. Now we've had and statements. Now we're going to kind of build on these and statements a little bit. Let's look at a contingency table though first. And we showed you one of these last week, and I think you fiddled with a couple of them in the homework, so you've seen these before. So what fraction of the US population 45 to 64 years of age have diabetes? Well, we go over to the diabetes column and we find the right age bracket, and we see that there's 13,400. And then we see that the whole population is 313,320. So this is in millions. That explains that. I'm looking at that like, what? So we have our 13,400,000 with diabetes in that age group over the whole population. So that's the fraction of US population who are 45 to 64 years of age and have diabetes. What fraction of population ages 45 to 64 have diabetes? Okay, so now, again, we're dealing with our of part. We have our 13,400,000, but our of, instead of being the whole population, is just that age bracket. So now we have 13,400,000 divided by 81,926,000. Okay, so that's the fraction, and that equals 0.164. That's the population age 45 to 64 that have diabetes. We're headed somewhere with this. So marginal and joint probabilities, though. So a marginal probability is a probability only related to a single event or a process, such as A. And a joint probability is the probability of 2 or more events or processes occur jointly, such as a P of an A and a B. So if these proportions are interpreted as probabilities for the randomly chosen individuals from the population, the value 0.014 in the first column. So basically this is the same thing, only instead of being we're talking about the probability of each of these boxes within the whole of the population. So 0.014 in this first column of the second row implies that the probability of selecting someone at random who has diabetes and whose age is between 20 and 44 is 0.014 or 1.4%. The entries in the 8 main table cells, so these 4 here. This is a total, this is a total, and this is a total column. Are joint probabilities, which specify the probability of 2 events happening at the same time. In this case, diabetes and a particular age group. In probability notation, this would be expressed as, well, for the 0.014 is equal to the probability of diabetes and ages 20 to 44. Okay. The values in the last row and column of the table are the sums of the corresponding rows or columns. So the sum of the probabilities of the disjoint events. So diabetes ages 20 to 44 and no diabetes ages 20 to 44. So you can't be both, right? So you either have it or you don't. And but that totals to 0.329, which means that the probability of being in the age group 20 to 44 is 0.329. Okay. The row and column sums are marginal probabilities. So they are the probabilities of only one type of event, such as age. So this is an age, and this is a diabetes or no diabetes. For example, the sum of the first column, 0.93, is the marginal probability of a person in the population having diabetes. So this is 9.3% is the probability of a person in the population having diabetes. Because this is the total of this column. Make sense? Okay. It's just practice. What is the interpretation of the value of 0.907 in the last row of the table? So right here. That is the value of 0.907 in the last row indicates the total proportion of individuals in the population who do not have diabetes. And the 0.097 directly above that. The value 0.097 indicates the joint probability of not having diabetes and being in the greater than 64 age group. Okay. So again, we're going to have this thing called the conditional probability. And you see this bar here. So instead of an and or an or, now we have a bar. What that means is the conditional probability of an event A given. So anytime you see that vertical bar, you think given. An event or condition B is the probability of A given B is equal to probability of A and B divided by the probability of B. Calculate the probability that a randomly selected person has diabetes given that their age is between 45 and 64. So here's our formula. We need to plug in the probability that a randomly selected person has diabetes. The probability of diabetes is A, and the probability given that their age is between 45 and 64. So our formula here, probability of diabetes given 45 to 64 is 0.043 divided by 0.261. Probability of A and B, so we found our intersection of those two events of 0.043. We found our probability of being in that age group, and we divide. So 0.043 divided by 0.261 is equal to 0.165. Calculate the probability that a randomly selected person is between 45 and 64 years old, given that the person has diabetes. So this time, we're working the opposite direction. Probability of that age group given diabetes. So you want out and you want to know the probability that the person is that age group, given that you found somebody who has diabetes. That would be 0.493 divided by 0.93, or almost 40, just about 46%. So pretty good. Yeah. Grab a hold of somebody that has diabetes, they're probably in that age bracket. Assuming random selection, of course. Okay. Got a lot of rules. Now, what if you don't necessarily know if this rule applies? So if you have A and B, they're two events, then we can use this probability of A and B is equal to the probability of A given B times the probability of B. If we're thinking about A is the variable of interest and B is the condition. So we can generalize that multiplication rule. So suppose that among the male population of adults 25 to 40 years of age, hypertension occurs 18% of the time. Assume that the population is 50 male, 50% female. What is the probability of randomly selecting a male with hypertension from the population individuals 25 to 40 years of age? So probability of A and B is equal to the probability of A given B times the probability of B. Let A be the event that the person has hypertension, and B be the event that they're a male adult between 25 and 40 years of age. So the probability of A given B is probability of hypertension given male, 0.18. Thus, the probability of hypertension and male is 0.18 times 0.50, or 0.09. So there we have it. So we have a lot of examples to do. There's a lot of to do of these. Okay. If the general rule wouldn't be necessary if the events were independent. So what we can do is basically test and see if probability of A equals A given B is equal to the probability of A, then we didn't need to do all of that anyway, which is kind of it's cold comfort given you've already done all the math. But it does give you some indication of whether or not these two events are independent, if it maybe is a little more complex than, cards or something like that. So this is basically, if they're equal, we can work our way to this if they're independent. Okay. So in the US population, 45% of people have blood group O. Suppose that 40% of Asian people living in the US are blood type group O, and the Asian population in the United States is approximately 4%. Do these data suggest that blood group is independent of ethnicity? So we could test for that since we have the probabilities. Let A represent blood group O and B represent Asian ethnicity. So if probability of A given B is 0.40, if it doesn't equal probability of A 0.45, then the two events are not independent than the blood group. And they don't. 0.40 does not equal 0.45. So they're not independent of ethnicity. Okay. Now you're going to get to a part of the chapter where they're going to talk about something called Bayes' theorem. Skip it. It's crazy. You don't want it. I am relatively certain that I've got the homework question that has Bayes' theorem deleted, but I thought that in a previous quarter as well, and the question was there again. So I need to look and make sure that it's not there. But if it is, then don't do it. Or just put in an answer and we'll figure it out later. So that's Thursday. We will do some questions. Wow, that was fast. And sure, you haven't interrupted me any, which is, I mean, it's okay. Well, okay. Then Thursday we'll work on homework and do examples and stuff. We've got the rules here.